So good morning. So this morning we are going to discuss chapter 6 of Arnold, which talks about the estimation. So in estimation, what we are looking here is we are trying to get an estimate of our parameters, theta or our mean vector mu, to be estimated by x bar. And our sigma squared, or in general sigma squared I, if it's a basis matrix is orthonormal already, will be estimated by sigma hat square. So before we go into this, let's recall some properties of estimators. First, we have the MVUE, or the minimum variance unbiased estimators, and MLE is a maximum likelihood estimators. So let T of X be a function of our x's, be a complete sufficient statistic, and S at T be an invertible function of T, then S is a complete sufficient statistic. So S here, S of T, where T can be a function of X. So pwede ra po na siya S of X kung ano siya, function of the original S. So X values or X observations. Or if you do some transformation on X and it is also a complete sufficient statistic, then your sufficient statistic is S of T, or S at T of X. So an example of that is an example of that is that I am referring for, say, if you have an X observation and you get the sum of XX. Now, the sum of XS is a sufficient statistic. No, this is a sufficient statistic, as well as it is a complete sufficient statistic. But if you convert this to the summation of x of I over n, which is usually our x bar, let me have some. So if we convert this to x of I over n, this is now your x bar. So this one, from x to this, that is your T of x. No, in our notation, that is our T of x. And summation of x of I is a complete sufficient statistic. Now, if you can find an S of T, so ibig sabihin, x bar now will be our S of T, or it is a new estimator derived by transforming T. So from summation of x of I, it becomes summation of x of I over n. That is your S of T. And if f of c is an invertible function of T, ibig sabihin, you can always go back to T after using x bar. So for example, we can always go back to the summation of x by pre-multiplying x bar by n, no? So this is, you can retrieve back summation of x from your x bar by pre-multiplying it by n. So it means that it is an invertible function of T. Then S is also a complete sufficient statistic. Ibig sabihin, x bar here is also a complete sufficient statistic. So a function of a complete sufficient statistic is also a complete sufficient statistic. Do you follow?
Yes, ma'am.
So sa atong notation, ang T of X will be the summation of X. Ang S of T will be X bar. So if summation of X is a complete sufficient statistic, then X bar, which is a function of T, or in our notation is S of T, is also a complete sufficient statistic on the condition that S there is an invertible function. Okay. Okay, lemma 1.1. Lemma 1.1 is the Le-Manchefei theorem, which is theorem 1.4 in chapter 1 of Arnold. So this theorem tells us that if S of X, okay, a function of X is a complete sufficient statistic, and T of S, or if you write T as a function of S, so kini siya na notation, bali siya ani, no? So here, this is a complete sufficient statistic. So this will be our summation of xi, and T of S here will be our x bar, or a transformation on the S. Kaya ang atong S kiniman. This is our S of X. So if T of S, aside from a complete sufficient statistic, it is an unbiased estimator, no? So kung kining x bar nato is an unbiased estimator, then kining T of S nato is ang MVUE, or a minimum variance unbiased estimator. So what is this theorem telling us, or the Le-Manchefei theorem telling us? So kung naa kay complete sufficient statistic, so kung naa kay summation of xi, so complete sufficient statistic man eh, this is a CSS. This is a CSS. And then kung naa kay makit-an na transformation, because summation of x is not necessarily unbiased, no? Pero if you can find a transformation on summation of S, which is unbiased. So for example, x bar is a transformation from summation of x, which we divide summation of xi by n. And this is an unbiased estimator. So kung mo satisfy na siya, if x bar is also a complete sufficient statistic by definition, no? Kung dinhi. So kini CSS man, transformation niya is also a CSS. So if you can prove that that new transformation of an CSS is unbiased, then that estimator x bar is MVUE, or a minimum variance unbiased estimator for your general parameter space, say tau of theta. So any transformation also. So for example, na kay theta, ang estimator ana for summation of x, utang nato total, no? Mao ni iyahang parameter theta. And then i-transform na nimo by tau of the total. So tau of total, which is your mu. That transformation there. Then it is also MVUE. Okay? So, unsaon paggamit sa Le-Manchefei, primero i-show nimo na CSS siya. And then katong transformation sa CSS man pud to siya, but you have to show that it is also unbiased. Once CSS plus unbiased, then it's MVUE. Okay, so that is how you use this theorem, Le-Manchefei. So two conditions to show, one is CSS and the other one is an unbiased estimator. Next, the maximum likelihood estimator. So T of X, or a function of your observations X, is an MLE for the parameter theta if the density function of your T of X is always greater than the density function of your parameter, for all parameter in your omega. So if theta hat is an MLE for theta, then any transformation on your theta will also be an MLE for tau of theta. So kung naa kay theta hat na MLE for theta, kung imong i-transform ning tau at theta hat, MLE po na siya for tau of theta. Okay? So maximum likelihood estimation or estimator will base its conditions on the probability density function. So when we solve for MLE, we look at the probability density function of the distribution of X. So in general, let us consider the linear model in which we have Y is normally distributed with mean mu and variance sigma squared I. Mu is in V and sigma squared is positive, where V is a specified p-dimensional subspace of Rn. And let A be an arbitrary S by N matrix. So S is also arbitrary. The dimension will be arbitrary. And mu hat and sigma hat squared is earlier defined in chapter 1. The mu hat is chapter 1. Chapter 5 will be the projection of Y onto V, and sigma hat square, which is the square norm projection of Y Y onto B perp over N minus P. But you can always write the square norm projection of Y onto B perp as the difference of the square norm projection of Y minus the square norm projection of mu hat. So in other words, you can write this as the square norm projection of Y minus the square norm projection of Y onto V. No, because mu hat is the projection of Y onto V. Now, theorem 6.1 in Arnold tells you that if we pre-multiply mu hat, so ibig sabihin, from mu hat, which is the projection of V onto Y, if we pre-multiply it by arbitrary matrix A, which will be equal to the A times the projection of Y onto V, and mu hat square are minimum variance and bias estimator of A mu and sigma square. So respectively. So ibig sabihin si mu hat MVUE na siya for mu. And if you do some transformation on mu hat, MVUE na siya for A mu. Okay? This is what this theorem is telling you. There is no transformation for sigma. Ang giingon lang ani na theorem is that for sigma hat square, which is the square norm of Y minus the square norm of mu hat square over N minus P, this is MVUE for mu hat square. For mu hat. For mu square rather. Or mu square. Sigma square. Sorry. And for MLE, mu hat is MLE okay, mu hat is MLE for mu, but dinhi sa MVUE, N minus P times sigma hat square is MVUE for sigma square, no? Kini ang iyahang MVUE. But for MLE, it will be N minus P sigma hat square but over N, no? Will be MLE for sigma square. Okay, so there is a difference in the MVUE and the MLE for the variance sigma square. Okay, so this is actually the same for MVUE, no? Mu hat is MLE for A mu. Okay. So for the proof of the first part, we know what we want for the proof of the first part is that A mu hat is MVUE for mu, A mu, for A mu, and and and
Uy, kuya. Naman kay photo paper gihatan na ko sa imo ha. Asa man ko mga photo paper, sticker paper. Lagi sticker paper naman ko gihatan sa imo ha. Wala man si grandma na. Wala na si grandma sticker paper. Katong akong gihatan sa imo ha. Tanawa dito sa box. Naghatag ko sa imo ha duha ka buok.
okay, can you hear me?
Yes, ma'am.
Yes, ma'am.
Okay, so where were we? N minus P sigma squared will be MVUE for hat, for sigma squared. So mao ni gusto nato sa A na part. Okay, let me first erase. Okay, so we know from theorem 5.1 that this is the distribution of our mu hat that is normally distributed with mean mu and variance. Because how do we define our mu hat? That is the projection of y unto v, no? So the mean vector is mu and our covariance matrix is sigma squared PB. So that should be here. So that the expectation of mu hat will be mu because that is mu, and the expectation of A mu hat will be, this is just an arbitrary constant of matrix. You can take it out of the expectation sign. So that is equal to A mu. And we can show that N minus P sigma hat square ni siya dapat. Sigma hat square is sigma square chi-square distributed central, no? So that you can show that the expectation of NP over NP over sigma square times sigma hat square is just equal to NP. Is this correct? So the expectation of N minus P over sigma square, sigma hat square, this is a constant with respect to expectation. So you have this is just equal to N minus P sigma square and then expectation of sigma hat square. But this is the one with the N minus 1, no? Or small n minus 1 na denominator. So this is just equal to sigma square. So cancel. So you have N minus P here. So that if we manipulate this, just add these two and then get the expectation of this, which is equal to N minus P, and then you have sigma square. So hence, both estimators there are are unbiased estimator, so that by the Le-Manchot-Fay theorem, since we know already that these are complete sufficient statistic, then both are unbiased statistics. So we can use the Le-Manchot-Fay to tell that A mu hat and sigma hat square are MVUE. So for MLE, that is 6.1b. So for MLE, we have to look at the density function of a normal distribution. So each of the y are normally distributed so that the density function of mu sigma hat is the product for each, no? 1 over 2 pi 1/2 sigma I from 1 to n exponential of negative 1/2 sigma square times the difference yi and mu I. So if you get the product of that, that will just be equal to the square norm for the this part here, and this part here will be raised to the n. Kay product na siya man, independent. So product of independent random variables. So that's why you have here n, and katong part na yi minus mu I, kay kada isa sa yi normally distributed man with mu I and variance sigma squared I or sigma squared. This part here will be the square norm of y minus in matrix notation or vector notation. And then kuhanin mo ang product ana sa iyang density. So that's why you have raised to the n here. And then you have to show this one to be a function of, this should be a function of mu hat and sigma hat square. No? So you know this relationship that the square norm from mu hat will be the shortest, or the length will be the shortest because it is nearest, no? So if you recall, kung naa kay vector y din man imo nang i-project sa subspace na V, the projection of y unto V will be the one closest, no? This is the closest. So for any competition y minus mu hat, siya ang any other competition value of mu, si mu hat mo ay pinaka duol or the closest that you have, or the square norm or the distance will be less than or equal the distance of any competing difference here, say y minus mu. Si mu hat lang ang pinaka closest, no? That is what this inequality is telling you. That is for all mu in V. Therefore, for all sigma, this probability density is maximized when mu is exactly equal to mu hat. And also for, so mu hat here will be the candidate for MLE for mu, and to get an estimate for mu square, sigma square, you get the density and then differentiate it with the parameter sigma. And then, so muna imong differentiation, but it is easier if you are dealing with exponential e to the something, no? Pag differentiate, masayon kung kuhaon nimo ang log of the density. Log of this will just be equal to the parenthesis. So if you get the log of the density, and that is equal to the log of the e to the something. E to the something. So which is just equal to, dapat log of the e to the something will just be equal to this term. So kini siya, magpabili na siya, and then the log of this, log of a over b will be equal to the log of a minus the log of b, no? And if you try to apply this, you will have this one. And then the log of e to the something is equal to the something there, which is this one. Okay, so this is from here, and this one is the log of the quotient. This is equal to the log of a minus the log of b, which is this part. And then you differentiate with respect to the parameter. That is how you maximize your function, no? You have a function, differentiate it with respect to the parameter, and then you equate it to 0 and solve for the parameter. So if you differentiate it with respect to theta, sigma squared, rather, this part here, this is a constant with respect to sigma squared, so this becomes 0. So ang mabilin, kinira, that is the derivative with respect to sigma square, and this is the derivative with respect to sigma square. And then you equate this to 0 and solve for sigma, and an estimate of sigma will be equal to, a sigma square will be equal to n minus p over n times sigma square. So you just isolate the terms here, sigma, and get the final answer. So I think you have many practices on that, of how to get a maximum value in your calculus classes, or in your probability classes, or maybe in your inference. Okay? Basta sa MLE, what you do first is to get the product of all the densities, then differentiate it with respect to the parameter, equate it to 0, and solve for the parameter. And the candidate there will be, the answer there will be an estimate for your parameter. So for C, it's the same procedure, except that you will be dealing with a mu. But that is very straightforward, because you already know that mu hat is an MLE for mu. So all you have to do is do a transformation on your density function. A mu hat ang imong gamiton for the MLE. So the proof of that follows from the definition of maximum likelihood estimators. So as corollary to that, so if we look at the coordinatized version model, sa ganitong coordinatized version model, if we have original y, which is normally distributed with mean, variance, sigma squared I, the coordinatized version will be n x beta, no? Sigma squared I. So in this notation, X is a basis matrix for V. Beta is the unique solution of the equation mu is equal to X beta. So your mu is X beta. So your mu hat will be an estimate X beta hat. And then your beta hat is equal to X prime X inverse X prime Y, no? Or X prime mu. So if beta is the unique solution for the equation mu is equal to X beta, and we let beta hat be the unique solution of mu hat, or equal to X beta hat, and C be an arbitrary S by P matrix, then C beta hat is MVUE. And it is also MLE for CB. So C beta hat is MVUE and MLE for CB. Okay, so the result of this just follows from the previous result when we try to solve it in the projection approach, no? Next, we look at another property. So ang atong mga gipang tan-aw na mga properties is first is a CSS, a complete sufficient statistic. And then we look at properties of unbiasedness. And then we look at combination of CSS and unbiasedness is NBUE. And then mga maximum likelihood na estimators. And another type of estimator is called invariant estimators. And then if we add criterion on the variances, then we say it is best. Okay. So first we try to understand what will be the definition of invariant estimators and when will it be to be a best. What are the conditions that it will become the best invariant estimator? So we now discuss best invariant estimators. These estimators were first suggested by Pitman and are often called Pitman estimators. So consider the problem of estimating an m-dimensional vector, a tau of theta, or a function of your parameter theta with a loss function. So equivalent, when we talk about invariance estimator, it is usually associated with a loss function. The usual loss function is the square loss function, or in general, the Mahalanobis loss function. So ang Mahalanobis loss function, if you go to the univariate case, that is just your square function, no? Okay, so let's recall unsa tong Mahalanobis loss function, or in general, what is a loss function. That was chapter 4 or chapter 3.
Chapter 3 siguro.
Chapter 3. Okay. So the loss function is associated with your estimator D with some parameters, say mu and sigma. And this is equal to the difference between D and your true value mu standardized by the variance. Maunang inverse ni siya, denominator. And then D minus mu. So kini siya, kining duwa, that is actually in univariate case, that is just D minus mu bale square, no? Or DI, or the differences between the actual estimator from your parameter mu. So this is your Mahalanobis loss function. So invariance will be associated with a given loss function. Okay? It is associated with a given loss function. So in general, mao ni atong theta dinhi. Mu sigma. Dinhi general lang siya. Okay? So let A be a set of possible values for tau of theta. A is often called the action space for this problem. And let G be a group of, okay? Now, there are conditions for a G to be a group transformation. So if you look at chapter 1, when will a set G or a set of functions to be a group, or when will it be considered a group na ay duha ka condition such that it will be considered as group. to the chapter 1. It will be a group if it satisfies while this function anyway, you just read pages 3 to na yung mga condition when it will be a group, no? You have to satisfy so that it will be a group. Usually it has to do with being closed, and the inverse is also in closed. So ibig sabihin, if you have two functions h and k, and you get the composition of h and k, both of h and k say is in capital H, then the composition of h and k should also be in capital H. So kung satisfy na siya sa chapter 1, pages 3 to 8, no? And then another thing is, if we have an h in H, if you get the inverse of H, it should also be in H. So if these two conditions, the composition and the inverse, are closed under the said operation, then we say that this group of functions here is a group, no? And it is an invertible function that is gikan din mupaingon nagyapon siya diha, no? So what is this telling us? There is no loss of information even if we do some transformation on our data set and in solving the parameters, no? So all you have to do is also do a transformation on your parameters. Say for example, if x and you have an estimate, say theta hat, for theta, if you do a transformation on your x, what will be the parameter now? It is still a transformation on your theta hat given by this g bar, no? So a transformation on the data is g, but a transformation on your parameter will be g bar. And these are all invertible. Ibig sabihin, kung si x mo at i-transform nimo, applyan nimo og transformation or a group of transformation on x, moadto ra gyapon siya sa x. At the same time, the same is true when we do a transformation on g bar. So it is just invertible, no? So there is no loss of information, and you can get all information about the parameter theta hat on the transformation on theta. So this is what this invariance thing is telling us, no? So it is invertible. So pwede ra ka mo retrieve balik sa iyaha as if you are just studying the original data set. Okay, so for example, if your data set is G and you did a transformation on X and we call it Y, then the density will just have the density of Y, but the parameter space now will be at G bar. So a transformation on X, what happens is you also will have a transformation on the parameter space. Also, if you apply a transformation tau on your parameter space by this G bar na group of transformation, and then that is just equal to applying a transformation G tilde or on the set A, no, the action space at tau of theta. And also it is telling us that the loss function incurred by doing transformation on the action space on your estimator D, in this transformation on the parameter space is still the same as the loss function incurred when you study the original estimator D and theta. So, ibig sabihin, in terms of loss function, walay na gain, wala po'y na loss, no? So, ang original na dataset na imong gisolban sa estimator D for theta. So, here, ang atong estimator, ano equivalent sa theta hat. Ang atong estimator D for theta, the loss function associated with that is just the same as the loss function if we tried to do some transformation on D and the parameter. As long as mo satisfy ni siyang imuhang kini imong mga G bar, G bar, and G tilde, dapat naana siya sa imuhang group of transformations such that it is just an invertible function that is from chi to chi, no? So to test whether an estimator T of X is invariant, so mo ni at imuhang mga set of transformation or group of transformation. Let capital G bar and capital G tilde bar be the set of all transformations of G bar and G tilde. We say that this estimator T of X is invariant. Okay? T of X is invariant. So, unsa nang T of X gani? This is your example. This is your X. One possible T of X is a summation of Xi. So, that is a transformation on your X. Or, pwede po S of T na siya. Or, S of T is a sufficient one. Wherein you can make it such a point, one conversion of your T of X is by dividing it by N, which is your X bar. So, in general, kaning transformation na gihimo nimo sa T of X, which is summation of X1, kining X bar, pwede ni siya i-name na to og T1. This is one transformation that we did with X. And X bar will be another transformation that we did on X, no? So any transformation on your data X or in your observations X, it is invariant under this group of transformation G. So ang atong group of transformation G can be si G bar na element sa G bar, or si G tilde na element sa G tilde, or in general, si G na element ni G. So si G, pwede na G bar, pwede G tilde. Okay? So this T of X is invariant under G if kung maghimot tag transformation sa atong X, no? Maghimot tag transformation sa atong X applied on T, then this is just the same as asa gani ang G tilde. This is G tilde is on your action space, no? Kini G tilde is in your action space. So asa nimo i-convert action space on your TX, on your estimator. For all G in G, so ang G in G nimo can be G tilde or G bar, and for all X in your data set or data space. So that is the definition of an invariant estimator. So when will it be best? when will it be best? So we say that T of X is best invariant estimator of tau of theta if T of X is an invariant estimator. So mo-satisfy siya dapat ani. Invariant na siya daan. And T of X is better than any other estimator. So how do we measure that Tx is better than any other competitor na invariant? So invariant gihapon ang iyang kakontra, pero kano sa man siya better? So the better or the best will be measured in terms of a loss function. So we choose a loss function, we compute the loss function of this T of X and any other competitor na invariant estimator. The one which will give a smaller expected loss, by the way, on the average, no? The expected loss is actually equal to a risk, no? The risk that we incur when we use the estimator. So expected loss function or the risk function, no? So if we put function here, then we will be looking at a risk function, and the risk function that will give the smallest risk. So if it gives the smallest risk among any other invariant estimator, then we say that that estimator is the best invariant estimator. So let's consider these problems of finding the best invariant estimator for A mu. So A here is an S by N matrix of rank S. And we consider a fairly general class of quadratic loss function. So quadratic loss function. So we just divide it by sigma square here. So the loss function here is D1 minus A mu. So ang atong parameter din this is your theta, A mu. So this is your parameter. So mangita tag estimator na D1. So ang kandidato ani is si A mu hat, no? Mao ni ato ang theta hat. So let D1 be an S by 1 vector estimate for A mu. So the general loss function here is given by this quadratic loss function given by this. So kinina part din mao ni ang ato ang sigma inverse sa ato ang Mahalanobis distance. So where H here is just an arbitrary known matrix. So this problem is invariant under group 1 of transformation. So the group 1 transformation is given by this. So pag check nato na invariant na siya mga group of transformation. So invariant lang siya ani na group of transformation. So unsa man ni nahitabo. So ang transformation sa imuhang estimator mu hat ug sigma hat sa mean pwede nimo adan og B man mao ni imuhang covariance matrix C squared sigma squared. And then sa parameter similar ra sila. Bale, ang transformation na imong buhaton, mag-add ka B. And then sa imuhang action space, ang buhaton nimo sa imuhang estimator D1 will be pre-multiplied by C, ang D1 plus AB. Now, we say that it is invariant if we apply if we find the loss function of that transformation kining sa imong action space sa G tilde o sa imuhang parameter space, ang loss function will be equal to the original, no? As if nag-deal lang ka sa original D1 and imuhang parameter space mu sigma squared. So, given this group of transformation here, ini siya. Let's see why it is invariant. It is invariant if we can transform the loss function of the transformation is just equal to the original loss function. Okay. So let's apply. Mao man ni ang transformation sa imuhang sa imuhang estimator na space. So let me write again the Mahalanobis loss function. So ang loss function L D mu sigma is D minus mu prime sigma inverse D minus mu, but ang atong sigma inverse din gina-consider is H over sigma squared. Okay? So kung kini ang atong transformation, ang atong D will be this one. So C D1 plus AB, then ang atong parameter will be C, man kini atong D1 will be A mu. Kaya mao man na atong gusto na parameter na estimate, this one. We are considering this as our parameter. So that will be A mu. So ang atong D1 din is A mu. Okay, plus AB, and then this part here, which is H over sigma, pero ang atong sigma is C squared sigma squared. So you have H C squared sigma squared. Then the same thing here, and this is your parameter. And then if you try to simplify that, makancel ning AB, and then kining C squared din makancel sa C ug C diha. No? C din man ang isa ka C na din no? Maning C squared. This is cancelled with that, and then ang isa ka C makancel sa isa ka C din So this will give you this one. And this is actually the original loss function at mu and sigma squared. No? So we say that A mu hat is the best invariant estimator of A mu for the given loss function under the group of transformation G1. So to see that, so mao ni imuhang T of X, T of mu, T of D, or T of X, no, sa atong notation. Or this is your parameter mu hat and sigma square. No, statistic estimators. So it is in an invariant estimator under G1, katong transformation na mag-add ka og component sa first, if and only if you can show this, no? So ang iyang transformation is mag-add kag B sa first component. So T at G1 at mu hat sigma hat, if you can show this, that it is equal to G1 tilde at T at mu hat sigma hat. Or equivalently, if you can show that T at this transformation, kay mao man ni na group of transformation imong gi-consider, this one. So inaani ang imuhang pag-transform sa iya ha, no? Mag-add ka og b sa min. So this is you add mo na imong mu hat, no? G at mu hat. Gi-add nimo at G1 at mu hat. Gi-addan nimo og b and pre-multiplied mu hat by c, and this is your variance. And if you can show that this is equal to c times, so i-applyan nimo og g tilde sa t at mu hat. So ang imong gusto is t at mu hat sigma hat g tilde. Unsa man ang g tilde? Kini ang g tilde nimo na transformation. Kini. So C at D1, pero imong D1 is mo na imong estimator. Okay? That the T of mu hat sigma hat square plus AB. Okay? So you always go back to the type of transformation that you are going to use, no? So in this example, your group of transformation is this one. Okay, kini G1, si G1. So, erase. Okay, mao ni imong group of transformation. So, to show that it is invariant, an invariant transformation, you have to show this, or equivalently sa atong G1, kini ang imong ipakita. Equal siya ana for all C greater than 0 and B in your subspace V. Okay, so note that we have shown that A mu hat is an invariant estimator for A mu. So, para mapakita nimo na best, invariant naman na siya with respect to loss function. Para mapakita nimo na best, you have to show a competing invariant estimator. So, mag-let ka say T of mu hat sigma hat be any other invariant estimator for A mu. Okay, so ang kompetensya nimo, ang invariant na si A mu hat. Man mo pili kag another invariant estimator of A mu. Si tawago na nimo og T mu hat sigma hat square. And then mo set ka og C greater than 0, say let it be equal to 1 over sigma squared. The choice of this is predetermined or arbitrary as long as this is greater than 0. Dipili ni na value to simplify things, no? And you have B here, the one that is added in your estimator to be negative 1 over sigma hat square. 1 over sigma hat times mu hat. Of course, the choice again. So originally, ang pag-solve ani class, generic lang ng mga C o B. Mangitan-aw sa final answer kung unsa ang mga values sa C o sa B para ma-simplify ang matter. Okay? And then, gi-reassign dayon. Okay, that is how you prove usually in mathematics. Primero, imo nang i-let as C lang. And then look at the final answer and then try to manipulate the final answer para ma-simplify ang imuhang equation. So actually ang atong gusto din ma-simplify siya in terms of the risk function, no? Kay gusto man nato best, so dapat mapakita nato na ang risk function associated sa competing na invariant function mas dako sa risk function associated sa imuhang gusto na estimator na A mu hat. So in general, dinhi na part, puros pa na C and B. And then, what value of C and B would simplify this was found out to be at 1 over sigma and negative 1 over sigma hat mu hat. And then, i-substitute. Mao na dayon ni ang flow sa imuhang proof. Anyway. So, if this is your C and B, and since T is invariant, by definition of invariant, then T at 0, 1. So, dinhi. So, kung ilisa ni nako og this part, so if this is 0 and this is 1, then this becomes, we want to show that this becomes C is 1 over sigma hat kana, and B is 1 over sigma hat mu then A, no? Or equivalently, you can write this in this manner. Okay, so C mu hat plus B equal to 0. Nga naman, kay ang imong C, denote pa nimo og 1 over sigma hat mu hat, man ang imong B, denote man nimo og minus 1 over sigma hat mu hat. Are you following?
Yes, ma'am.
So kini siya 0 gina siya, yan ani na scenario man, kini siyang C sigma square, ang imong C square na nimo 1 over sigma hat square. Man, this is sigma hat square, so that is equal to 1. Okay? Are you with me?
Yes, ma'am.
Yes,
Ng
ma'am.
T at 0
Yes,
watt.
ma'am.
Or equivalently, rewriting it, i-isolate ni nimo LCD aning duwa, so i-multiply ni nimo by sigma hat, and then balihin ni as plus A mu. So, mo-follow ra na siya. So, an equivalent version of your T's mu hat sigma hat square is sigma hat T01 and A mu hat. Now, our aim here is to find the risk associated with A mu, or the expected loss function associated with A mu, and the risk associated by tau mu hat sigma hat, no? So ang gusto nato, kining risk ani associated ani will be greater than the risk associated sa A mu. So we see that T is completely determined by T at 0, 1. Kini ba? Kini na value here is completely determined if we know this, no? Because it is a function of this plus ang ato ang competing estimator. So if we can show that the risk associated by this term here is greater than 0, bali, positive ang iyang risk. And then this competing invariant estimator is, the risk associated with this is a function of 2, which is a value which is greater than 0, and the risk associated sa A mu. So, ibig sabihin, mas gamay ang risk associated sa A mu. Okay? So, again, I told you that the risk is actually an expected loss. So, what you do is, you get the risk of T, and then you get the expected loss function, no? Associated with tau of mu hat and A. Tau of mu hat and sigma hat square. So, so this is your D1 minus your parameter. Okay, so this is your D1 minus your parameter. And then you separate the terms here. So kung imo nang i-get the transpose here, so mo ni siya dinhi, man kini siya iuban dinhi. Okay? And then you group this one and this one. So you have this and this one. And then middle term. So may tabo ani na naman ako. This part here is sigma hat P01 prime plus A mu hat minus A mu prime. Okay? And then, so muna siya A prime plus B prime H and then A plus B. No? So, imo nang i-multiply ka na, paingon dinhi. Pagkauman, kini na pod. So, nanakay A prime H plus B prime H. And then A plus B. Then, imo nang i-multiply diha. Huwag ka na. And then, kini, kini times ka na, man times kani, man kini dayon times ka na, no? So, you will have 4 terms. Are you with me?
Yes, ma'am.
You will have 4 terms. So, and get the expectation. Kini ang first term ug ang second term, man kini ang middle term. No? Duwa siya kabuok na inatog itsura. Okay. So, after simplifying that, and we know that mu hat and sigma hat square are independent. We have shown that in chapter 3. That they are chapter 5 that they are independent. And you know in general that the expectation of mu hat from mu will be equal to 0. That is similar to the concept that xi minus x bar is equal to 0. No? So kinina ang imuhang estimators ng mga mu hat minus the general mean. This is, you know that this is equal to 0, no? So summation of x sub I minus summation of x bar. But you can write this as n x bar summation of x sub I, but n x bar is summation of x sub I. So x sub I minus x sub I, that is 0. So in general, if you are trying to get the difference of your actual value from the average one, that is equal to 0. And then this is the risk associated to your, or the expected loss. Mao man ni ang loss function kung kini ang imong D1, no? This is your D. Mao ni ang associated loss function if you are using a mu. This is the expected loss. So if you look at this, component siya sa, this is your risk associated when using a mu hat. And what we are looking at is this, but this one is just 0. So mawala ni siya. And if we can show that this is a positive term, not a negative term, then we are assured that the risk associated of any competing invariant estimator of A mu will be positive or greater than this risk. But since this is not negative and T is not equal to A mu, so it means that this term this is always positive. So this expectation here is, of course, sigma squared is positive, sigma hat square is positive. So this term here is always greater than 0. So ibig sabihin, a value equality is attained by a component which is greater than 0 and the risk associated when using a mu hat. So it means that for any competing unvariant estimator, the risk associated with that is greater than the risk associated when using a mu hat. Hence, a mu hat will have a smaller risk than any other invariant estimator, and thus it will be a mu hat will be the best invariant estimator for a mu. So as a corollary to that, if we use beta hat as our estimator for the coordinatized version of the linear model, b hat will be the best invariant estimator under this loss function. So it's always associated with a loss function and a group of transformation when we talk about invariance. And when A in our estimator, a mu man, no? A mu hat for a mu, when A is exactly equal to x prime x inverse x prime mu, so mao ni imuhang beta, no? So that is how it is related to, that is why we always use a mu, no? A mu. Not just mu. Mu is only used when you are in the univariate case, but when we are dealing with vectors already, bali, one data set lang na siya. But when we are dealing with vectors and matrices already, if we have basis matrix, then a mu ang atong ginagamit because in matrix notation, the a there can be, in terms of basis matrix, will be your x prime x inverse x prime mu na dayon for your or an estimate of a mu, which is x prime x inverse x prime mu. So this is mu hat. Okay, so if we have another type of loss function, so for example, dito na pud ta naka-estimator pero ang imuhang loss function in ani. So lahi na pud na ang group of transformation. So ang group of transformation will depend on your loss function, no? So if this is your quadratic loss function, in ani ang pagka-define sa imong quadratic loss function, then the group of transformation will be G2. So the transformation on your parameter here, ganina kay ano man to, sa itsura gani din he, CAD plus AB, no? So if you are going to use this loss function, kini na pod ang iyang transformation ra, C squared D squared, D2. Okay, C squared D2. Mo retain lang gyapon ang imuhang para sa parameter and estimator space, but the action space will just be C squared D2. So that if you try to apply the loss function using on the transformation G2, you will still get the original function. Okay? So kung inani ang transformation niya class, mao man ni ang mugawa sa imuhang katura man siya D2 over sigma squared minus 1 or D2 minus sigma squared quantity square over sigma to the 4th. Okay? Pero ang imong transformation is in ani. Okay? Sa imong space. So this is invariant under this loss function and this group of transformation G2. And for our estimator in terms of variance, the best invariant estimator under group G2 with loss function L1 will be this one. So if you recall, ang sigma squared is MVUE for sigma squared. And it is also MLE, no? Dili. Ang MLE is N minus P sigma squared over N, no? This is the MLE for sigma squared. Pero kung best invariant estimator, may mo na siyang N minus P plus 2 sigma squared. This is the BIE or best invariant estimator for sigma squared. But then again, it should be specified that it is a best invariant estimator under the group G2 and under the loss function L2. So dependent ang invariance sa imuhang group of transformation and loss function. Are you following?
Yes, ma'am.
Yes, ma'am.
Vary ang mga estimators for our variances depende kung unsa imong gusto. MBUE ba, MLE ba, or invariant ba siya? No? So you have different formula for the estimator. And actually, the proof of that is exercise B2. You can have it exercise as solving, but I will not anymore give that because you will study for chapter 3. Please do good in chapter 3. Okay. And then both the MBUE of sigma squared and MLE of sigma squared, this is the MLE for sigma squared, are invariant estimators. So, and hence, the best invariant estimator is better than either of these estimators, at least in the quadratic loss function. Therefore, the MLE and MBUE are inadmissible for this loss function. Okay? So, unusual kayo ginagamit ni siya ini na estimator, bihira na ninyo makitaan because using sigma hat square and n minus p over n sigma hat square is also an invariant estimator for at least a quadratic loss function. So mo ang usual na ginagamit is either the MBUE or the MLE, depende on what procedure that you want to apply in your analysis. So I will stop there because the next will be confidence and prediction interval. So this is related to confidence interval. So we will discuss that next meeting. We still have the Gauss-Markov theorem. And after discussing the Gauss-Markov theorem, then that will be the end of chapter 6. Do you have questions?